Welcome and hello. This is a video exercise in WRIMS, and I'm titling this exercise Simple Water Allocation. So what I have on the screen here is the WRIMS interface. We'll get to that in just a moment. I first wanted to introduce this exercise with a diagram I have sketched out right here on the screen. This is a very simple model schematic of a river system with some demands. As you see on the far left, we have nodes 1, 2, 3, and 4 representing a river system. And then from nodes 1, 2, and 3, we have diversions down to our farms. That's where we have our demands for farms 1, 2, and 3, respectively. All right, the next slide actually identifies different decision variables in the form of the flow through the channel, C1, 2, C2, 3, C3, 4, and then the outlet, as well as the diversions are also decision variables, the diversion to farm 1, farm 2, and farm 3. This I_1, this is the inflow into the system, into node 1 here. That is not a decision variable. We actually know that value, so we'll consider that a state variable. All right, so keep this diagram in mind. And the problem statement that I want to pose for this exercise is right here. Boom. Based on the data table. Oh, yeah, I also have to show you the data table. So here is the data table. Let me move that out of the way. And then hopefully I can get this all on the same screen. Farm 1, 2, and 3. Those three farms have an allocation of 5 CFS, 8 CFS, 13 CFS. And then this 20 CFS refers to the in-stream flow requirements downstream of these three farms, which I'm associating with node 4. In this column 4 here, I have the priorities listed. So the top priority, number 1 here, is the in-stream flow demand of 20 CFS. And then after that, the next highest priority is farm 1 with its 5 CFS demand or allocation as I'm putting it. And then after that, the next priority is farm 2, and then finally farm 3 has the lowest priority. Now, in the case of WRIMS, where the optimization seeks to maximize the objective function value, these priority values won't really work for using them as the coefficients in the objective function value. So what I'm going to do is just add a new column here called weight. And what it's going to do is be based on the priority. So I'm going to create a weight based on these values and basically just reverse the order so that the weight is highest for the highest priority, because the highest priority is 1 in this instance. So I'll just arbitrarily say this is 50. The next weight is for the next highest priority demand or allocation will be for farm 1, and I'm just going to set that to 40. And then let's say this is 30 and 20. So you see what I did there? The objective function value actually gets the most improvement by satisfying the in-stream flow demand, the 20 CFS, downstream of node 4. After that, it wants to satisfy the allocation at farm 1 because it gets 40 weight, 30, and 20. So these numbers are pretty much arbitrary, but it's what I chose, just as long as this is the highest number for the highest priority and then the lowest weight for the lowest priority. All right, so with that out of the way, let me move that over here. The next slide actually includes a table with those allocations and the weights that I just created. Again, these allocations, you can think of them as demands, and then the weights, these will be the coefficients that we use when we define the objective function. So that's coming up a little bit later. Again, okay, so now with that, we can go ahead and bring up the problem statement, and here it is. Based on the data table that we just provided and the diagram, the different demands, the allocations, and so on, the question is, what is the flow in this channel 1, 2 when the inflow is 28 CFS? And then also, secondly, part B, what is the flow in channel 2, 3 when the inflow is 50 CFS? So you can scrub back to look at the diagram. The answer, by the way, is 23 CFS and 37 CFS. I'm going to show the answer right now. It's not a secret. I'm also going to show it in the diagram. But then what's most important for this exercise is we're going to use WRIMS and build a model from scratch to answer this question and basically solve for the flow rate in every single link of the network. All right, so here's the PowerPoint. This right here is the flow through the channel for the final solved algorithm. This is the optimal solution when we have an inflow of 28 CFS. And then the next slide includes the diversion flow right here. So again, when there's 28 CFS entering the system through the inflow as the state variable, Then the downstream flow requirement of 20 CFS is satisfied. The farm 1 allocation or demand of 5 CFS is satisfied. And then the farm 2 demand or allocation of 8 CFS is partially satisfied. We have enough extra inflow to partially satisfy that with 3 CFS. And farm 3 gets no water. So then the next slide just highlights this particular C12. This is the decision variable. It's the answer to our first question. What's the flow in this length when we have a 28 CFS inflow? And then part B is when we have 50 CFS. These are our answers. And then the next slide shows the diversion flow. In this situation, 50 CFS inflow is enough inflow to satisfy all the demands, 20 downstream, and then 5, 8, and 13 for the demands at farms 1, 2, and 3, respectively. And there's even 4 CFS extra, which I've actually changed this 24. I've divided it into 20 and 4. You'll see why I did that later. But back at one of the earlier slides, I've divided the outflow from node 4 to be 2 parts. There's O underscore 4A and O underscore 4B. O underscore 4A has a maximum of 20 CFS. It's a similar constraint that I used for the diversion because I don't want the linear programming problem to incentivize or be rewarded for more than the 20 CFS in stream flow. So the 4 CFS extra in that part B is assigned to O underscore 4B, because there's just really nowhere else for the water to go. So enough talking. Let's go ahead and start building this model in WRIMS and solving it and seeing how that works. In the description of this video, I'm going to include links to a number of different lesson videos on WRIMS that go into a little bit more detail about the individual steps I'll be covering in this exercise. In this exercise, I'm going to go through them a little bit faster, sort of assume that you're familiar with those topics or you've seen those videos. But if you need more detail on specific steps in this exercise, check out the videos linked in the description of this video for a little bit more detail. All right, so the first step is to create a project directory, add it to WRIMS, and then create a launch file. Here is my project directory. So this is the path up here, exercise to project. It's completely blank at the moment, but it's ready to go. So what I'm going to do is come over here to WRIMS, right click, new, project. Okay, so it is going to be in general, project, next. I'm going to give it a name. It's going to be called E2, simple water allocation. Now for the path, I'm going to unselect this directory and then paste in the file path on my computer to the directory that I want that project to be stored in. Okay, and this path needs to have no spaces. Once again, here is that directory. I'm going to just highlight and Control C to copy the path to my clipboard. Come over here, paste, and then that's good. So I'll click Finish. All right. Over here, I have nothing in my project directory, and that's fine. So we're going to go ahead and create our launch file, and then after that, we'll set up the file structure and then add all the code to build the network. Going to be called E2 launch. To do that, just go ahead and right click and then come down to Run As, Run Configurations. Okay, let me resize this. In this left panel, go down to the bottom item, WRESL WRIMS 2 application. And then to create a new configuration, go right click new, or with this selected, you can just click on the new button right here near the top. This is going to create a new application, or sorry, configuration. And at the top, I'm going to give it a name. It'll be called E2 launch. The study name, I'll call it the same thing. Author, date, description, I'll leave that blank. Now for the main WRESL file, this is going to be a path to the main WRESL file, and it's best that this is a relative path. It improves the portability of the program in case I need to send it to someone else. I'm going to go ahead and just paste in the values for main WRESL file and also the .dss files. Even though we haven't even set up the file structure yet, I'll show you what that's going to be in just a moment, and it will be consistent with what we're typing in here. So I have my decision variable DSS file, my state variable DSS file. I'm not going to use any initialization files or groundwater folders or part A or F. That's fine. We're going to use a 1 month time step, and this is going to be for the water year 1922. So I'll leave the start time as it is, select 1922, and then that will be the last month of that water year. Okay, so that looks fine. The other thing we need to do here is come up to Common as the tab and then select on Shared. And then I'm going to just paste in the path to that particular project. All right, so that should save the launch file in my project directory. Let's see if that works. So I'll click apply. Okay, so yep, it looks like it came up. Here's the project directory. I have the launch file and then the .project file all ready to go. And now, according to my notes, what I want to do is set up the directory structure for my project. So here is the project directory. Here are the two files that we already have saved. Next, what I want to do is create a file and folder structure that is right here. I'm not saying this is how you have to do it. This is just how I've done it with a previous lesson, and I'm going to do it with this exercise as well. We're going to have a folder for DSS, and it's going to contain two DSS files, state variables and decision variables. And then I'm going to have a directory for run that will contain the main WRESL file, as well as another subdirectory called system, which will contain all my .WRESL files. All right, so I'm going to go ahead and set this up right now. As I mentioned, here are the two files that we already have saved in the main project file. Let's start by going right-click, New, Folder. This will be the DSS directory. Okay, and then the next directory will be Run. So let me just call that Run. Inside the DSS directory, I'm going to create a file for the decision variables. So text document dv.dss, and then OK. And then for state variables, so that'll be for the inflow. Right click, rename sv.dss. Okay, that's set up. All right, within the run directory, we want our main WRESL file. So new, and then text document. This is going to be main.wresl. Don't need that. Okay, thank you. And we want a directory called system now. So right click, new folder, system. We go inside the system directory. Now we're going to define 7 different WRESL files for different parts of the program. Now, there's nothing stopping me from just defining everything in the same WRESL file, but as the model gets larger, it's probably best practice to subdivide the model into separate parts that make sense based on the name of the file and the name of the folders as well. Okay, so let's get started here. Right click, new, and then next document. Let me just delete the extension. Okay, so there's ARCS channels. I'm just going to right click. It's a little bit faster. ARCS demands, just like that. All right, so I've got those all set up, just all blank files, 0 kilobytes in size. So let me go up to the run directory and then up to the main project directory. What I'm going to do next is start by defining the inflows and the demands. So inside this DSS directory, we have our state variables for inflows and demands. I'm going to define that data in DSS view directly. So let's fire that up. I've opened DSS view up, so I'm going to go File and then Open. Here's the project directory. Here's the DSS file. Here's the decision variable.dss. Nothing to do here. It's empty. This is where our decision variables will be written to after we run the program. So let's go File and Open. Now the state variable, sv.dss. Currently, there's no paths in here, and that's what we're going to create right now. So I'm going to go up to Data, Manual Time Series. I'm going to create a time series data set to represent the inflows and the demands for our model. I'm going to start with the demands here. And instead of including in the individual paths, I'm just going to paste in the path name here. Oops. There we go. And then tab, and then the individual parts to the path name have been added in right here. Project, that's just a generic term for project. Whatever your project is, you can type that in there. AWF1, this is the applied water to farm 1. So just think of this data as the farm 1 demand. Next, I'm going to type in the beginning of this time period, which is going to be the first year, the first month of that water year, 1921, and then the start time will be 24 hours. So this is like the last hour of the month. The units will be in CFS, and then for the type, I'm going to use period average. What I defined in the configuration was a 12-month simulation on a 1-month time step. So there's probably different ways to do this. I'm just going to define a constant demand for 12 months to this farm 1. So the farm 1 demand is 5 CFS. Enter. Okay. So I'm just going to type 5 in here 12 times. Oops, 13 times. Okay. A couple extra, it won't hurt. And then that looks good. I'm going to go ahead and hit save. All right. So this path has been saved. Here is the data. So it's just constant 5 CFS demand or allocation to that farm 1. I'm going to repeat this process for farms 2, 3, and then also the outflow for AW underscore O4A. You'll see what I'm talking about in just a moment. A faster way to add a path like one we just created without having to go through all those steps is just to go right click, duplicate. And the only thing I need to change is a few things. First of all, part B is going to be F2 for farm 2. And then that's cool. Click OK. Here's the new path to farm 2. Now I'm just going to go right click and edit. Now I can just change these numbers because we have a constant demand of 8 CFS. So I can just click 8 for the first row and then highlight all the rows, right click, fill, and then repeat fill will basically take the value from the first cell and then paste it into all the other highlighted cells. Okay, boom, that's how that works, and save. Okay, thank you, close. Let's do the same thing for farm 3. So right click, duplicate, AW underscore F3 is my part B now. Okay, thank you. Here it is. Let's change the value now up to 13 CFS. So edit, type in 13 for the first month. Let's highlight all the months and then fill, repeat, and okay. That's done. File, save. Okay, close. Now I want to do this one more time to represent the in-stream flow demand, which isn't quite the same thing as a farm, but I'm modeling it similar to a farm in this context. So just work with me at this point. I'm going to go right click and duplicate just as we've done before. And instead of F3 or any farm number, I'm going to call this capital O for capital A. All right, tab off and OK. OK. I'm going to change the value in this data to 20 CFS. Right click, fill, repeat, and that looks good. So file, save that. Now there's one more path I want to add to this sv.dss file for state variables, and that is the inflow. I could probably create two separate configurations and then run two separate models where one is part A with 28 CFS, the second is 50 CFS. I'm just going to combine it into 6 months of 28 CFS and then 6 months of 50 CFS. So I could just run the model once and then look at the results as they change from 28 to 50. So to do that, I'm going to just go right click and duplicate. Okay, so for part B, what I'm going to do is I'm going to call this, for part A, I should probably mention AW underscore is one of a number of different demands DWR uses for calcium model, which means applied water. And there's a lot of other prefixes here instead of AW. Like, for instance, if you're not using water for a farm, you can use water for a city or an industry or whatever. I don't know all of the prefixes at this moment. I'm not going to pretend to. So I'm just going to use AW, even though it was for in-stream flow demand. I recognize that's probably not the exact correct way to do it. But as far as running the model and getting the numbers to come up correct, it's insignificant. All right, so for inflow, I'm going to use the prefix I, and then I'm going to say I underscore 1, so the inflow to node 1. I know that's correct. And then for part C, I'm going to call this inflow. So these part C and part B values, I will need these values to match up exactly a little bit later on when our code references the inflow time series dataset and the demand or the allocation time series datasets. Okay, so I'm going to hit tab and then click OK. Okay, so here is the data we want to define for our inflow. I'm going to say 28, 28, 28, 28, 28, 28. That's fine. And then 50 for the second half of the year. Again, probably not the best way to do it. There's probably multiple ways to do the same thing, but this is going to work out for us. All right, so we are done defining our state variables. That's our inflow and our demands. The next step is to enter data into those WRESL files. So if I go up in my project directory, here in the run directory, system directory, I have these WRESL files, starting with ARCS channels. So this is where we'll define the channel data. So right click and open. It opened on my other screen, but here it is. I am going to also open all the other files right now just to save some time. So file, open, and then all of these as well, and open. So across the top here of my Notepad++, I have all my files open and ready for editing. Let's go back to the first one. All right, let's go ahead and start with ARCS channels. I'm going to just paste in code, like I mentioned, and just talk about it to save some time. What we're doing here is we're defining the different decision variables in the main river reach. So channel 1, 2, channel 2, 3, channel 3, 4, and then O4A and O4B are both the sum of those two basically create the total flow that is leaving node 4. So 1 to 2, of course, is from node 1 to node 2. 2 to 3 is from 2 to node 3. Here is that diagram just to real quick to provide a quick reminder. We're defining these decision variables in the main channel, or you may call it a river, for instance. So that's where that is. Okay, the next file over is arcs demands. Here is that. This is a state variable. So what we're doing is we're referencing part B, AW underscore F1, and part C, applied water, from that state variable file. So this particular path here is going to be the constant 5 CFS demand or allocation. The next line down is for farm 2. That's going to be 8 CFS, farm 3, and then O4A is the 20 CFS demand, which has the highest priority. So there's that. The next file over is arcs diversions. And then here's that code. I'm going to unindent. So there's that. And then save. All right. So these are 3 decision variables again. This time it's for the diversion to farm 1, farm 2, and farm 3. The STD here basically means that it's sort of the standard decision variable that can be non-negative, or I should say is enforced to be non-negative. And then channel is the kind, CFS is the units. Okay, so the next file over here is arcs inflows. This is similar to the demands, where we basically reference the time series for that constant either 28 CFS in the first half of the year or 50 CFS in the second half of the water year. I1 is part B, and then inflow is part C of that path in the sv.dss file. The next file over here is constraints underscore continuity. In one of my lessons, the file was called constraints underscore something else, connectivity, I think. But continuity is what I'm going to go with here. I just like the sound of that. Basically, it enforces mass balance at each of our nodes, 1, 2, 3, and 4. So cont n1 is the continuity constraint at node 1, and we have the inflow minus the outflow equals 0. Now, all of these are going to equal 0 because there's no storage. This isn't a reservoir, it's just a node where there's no storage. So if we wanted to, again, pick on this first constraint just as an example, and then bring over the model schematic real quick. Here's our node 1. We have inflow coming in, and then the different flows leaving this node are C12, and then the diversion here to farm 1. So that should be the exact same variables that we have here, inflow and the outflow. All right, so there's that. Next file over here is the constraints diversions. I'm going to paste that data in there. And then, so yeah, keep in mind that when we have constraints, we use this keyword of goal. It's not an objective, it's a constraint. And then also keep in mind when we see a less than, it really means at most. So these two values can be equal. And using the optimization, they should be equal if they can be, because we're trying to maximize the objective function value. And we have positive coefficients associated with each of these for decision variable values, which we'll get to in the very next file. But I'm calling these constraints max diversion, max diversion, max diversion, and max diversion to farm 1, 2, 3, and then also it's not quite a diversion, but I'm just going to call it max diversion O4A. Right, the next file over is our objective function. So here's that. Oops, got the file name at the top. We use the keyword objective right here. Just clean this up. And then the name of the objective, I'm just going to say is OBJ. Basically, it's a sum product. So here is the coefficient. We have 50 as the highest coefficient because this is the highest priority. We want the linear programming to honor the flow through this O underscore 4A decision variable the highest. And then second highest would be our second priority to farm 1, farm 2, and farm 3. And then the last file right here is our main WRESL file. This is not in the system directory. It's up in the run directory, one level higher. But what we're doing here is we're referencing all of these WRESL files, which are in the system directory, which we just defined. So demands, inflows, channels, and so on. Demands and inflows, these are the state variables, which reference the time series data in that sv.dss file. The next 2 lines down are the arcs, the channels, and the diversions. So this is where we define the decision variables. And then the constraints are in the next 2 files. Now we could put all of this into one single file, but it makes sense to start to segregate the different code blocks into different files just for the sake of keeping things organized, and also different folders if we needed to. So there's that. And then finally, the objective function was defined, and we put that last after the constraints, decision variables, and state variables. So that looks good. I'm going to go ahead and save all. Let's go back to our RIMS now and see if this works. So we have our file structure right here. I'm just going to refresh. Okay, that's fine. And then right click and run as, and then launch. Okay, so let's there might be an error here. Okay, I realized I just misspelled this file name, constraints continuity. I mean, it's spelled correctly here, but the actual file itself was misspelled. So one moment while I fix that. Yeah, I'm missing an S right there. Oops, 1 second. Just add that back in. Pretty good debugging error message, so that's appreciated. And I realize I also misspelled constraints right here, so I'd probably get the same error message. Let me just add my S, diversions. Okay. Oh, and then actually, this is also objectives. This is supposed to be plural, objectives. Okay. All right. I think that should work. Let's go ahead and see if that runs now. I'm going to right click and clear out the console. And then let's see, right click and run as E2. Okay. So run. Oh, it had an error message again. 1 second. What it's telling me is that it's missing an equal sign at the expected open bracket in my objectives.RESL file. So let me open that up. Here's the RESL file, line 1. See, this is position 14. So apparently it wants an equal sign right here. Let's see if this works. This definitely is not in the documentation anywhere I've read or in my preparation, but right click and then run as, launch. Oh my gosh, it's working. Okay, so it looks like it ran. That is strange. So what I did there was just add an equal sign. Yeah, that is not in the documentation anywhere. For instance, I'm looking at this documentation right here, and it says objective, and then there's no equal sign here. Okay, let's take a look at the results and then finish this up. So here is my DSS view. I got onto the screen here. I'm going to click on dv.dss, and then let's just go up to view, refresh the catalog. Boom. So here are our decision variables. So we have C12, C23, C34, and then here is O4A and O4B. So that's the flow in the main channel. And then right here, D1, 2, and 3 to farms 1, 2, and 3 is the diversion flow. So I'm not really sure how to best look at this. Keep in mind, what we want to do is match up the results with the actual numbers here. So in the first half of the year, for instance, when we had 28 CFS for our inflow, that's 28. The main channel should have 23, 20, 20, and 20. The diversion should have 5, 3, and 0. So let's go ahead and look at for that data. I'll just go ahead and highlight all these records and then click on the table button. Okay, and here we have the 23, 20, 20, 20, and then the diversion is 5, 3, and 0. And then downstream is 20 and 0. So that makes sense. We are prioritizing that 20 CFS downstream the highest. So there's that. Farm 1 gets its 5 CFS, its full demand. And then Farm 2 gets 3 out of the 8 CFS allocation. So that's true for the first half of the year for an inflow of 28 CFS. The second half of the year, when we have a total of 50 CFS, all farms get their full allocation or demand. 5 CFS to farm 1, 8 to farm 2, and 13 to farm 3. And then the full downstream flow commitment, of course, with 4 additional CFS. So looks like 46 in that case would be the sum of the demands plus the 20, because 50 is 4 more than 46, and that's why we have 4 extra CFS to budget for. So we could look at the graph and everything, but looking at the table here is sufficient for me to satisfy that we've solved the problem using the WRIMS linear programming model as well as the WRESL language based on the constraints and the continuity, and running that in our WRIMS application.